All right, we're taking a look at the energy concepts, questions for the energy section of our unit. So the first question was, how can kinetic energy be increased and how can it be decreased? Well, first we take a look at our kinetic energy equation. So kinetic energy equals 1/2 mv squared. Well, the only thing we can do to make kinetic energy get bigger or smaller is to manipulate the variables that are in the equation. So that means if we want to make it larger, we either have to make the mass larger or the speed larger. If we want to make the kinetic energy smaller, we either have to make the mass smaller or the speed smaller. And here's how that would look. If I have a train and I have a car, and let's assume they're both moving at the exact same speed, the train has a much larger mass than the car. So the m is going to be much larger in the equation 1/2 mv squared, and that's why you're going to have a much larger kinetic energy with the train. If you want a smaller kinetic energy, you would want a smaller mass, because a smaller mass is a smaller kinetic energy. When it comes to speed, if we assume the planes are about the same mass, the jet's going to fly much, much faster, and as a result, the faster speed is going to result in a much larger kinetic energy. If you want a smaller kinetic energy, you want a slower speed, because that's what you'll get. So if you want a large kinetic energy, you want the largest mass and the largest speed possible, and if you want a smaller kinetic energy, you want the smallest mass and the smallest speed possible. So now we can move to number 2. How can gravitational potential energy be increased and how can it be decreased? Again, we're going to take a look at our equation. Potential energy is made up of m, g, and h. M is the mass, g is 9.8 here on Earth, so that's not going to change, and then we have the height. So again, we have our 2 variables that we can mess with to change the potential energy. First, the larger the mass, the larger the potential energy. So if I have a bowling ball that I put up on a shelf and I have a baseball that I put up on the same shelf and they're sitting next to each other, the bowling ball has more potential energy because it's got a lot more mass than the baseball does. When it comes to the height, the higher you lift something, the more potential energy it's going to have. So if I'm up on top of a mountain, I'm going to have a lot more potential energy than if I'm just up on top of a hill. So the higher you go, the larger the potential energy. The lower you go, the smaller your potential energy. Number 3, you lift a book over your head, and according to physics, you did work on the book, and work is giving energy to or taking energy from an object. So if you gave the book energy, why isn't the book moving? Well, the work energy theorem says that the total work, the net work done on an object equals the object's change in kinetic energy. And since the mass isn't changing, it means that it's going to be going faster or going slower if you do net work. But here's the thing. Even though I do work by lifting, I don't do total work. I don't do net work because gravity is pulling downward. So in order to lift this book, I lift with the exact amount of weight that the book has, which is equal to the force of gravity. Weight and force of gravity are the same thing, which means all the work I do in lifting the book, gravity tries to take that energy away by exerting a force downward. So I can give it potential energy that way by lifting it up over my head, but I'm not giving it a change in kinetic energy because no total work was done because gravity tried to take all the work that I did on the book tries to take it away. So I do positive work lifting it up, gravity does the same amount of work but in the downward negative direction. So that is why there is no total work and it's not moving once it's sitting over my head. Number 4, if you push your desk across the classroom, according to physics you did work on the desk. Since work means you gave the object energy, why doesn't the desk have more energy than before you started pushing it? If you just slide it across the room at the beginning, it had no potential energy because it's on the floor, and it's got no kinetic energy because it's not moving, and when you're done sliding it, it's still sitting on the floor, not moving. So, what gives? Where'd the energy go? Well, the key to that is friction. The friction on the book, or excuse me, on the desk, when it slides, is going to take all that energy away. So you give it kinetic energy when you give it a push and you slide it, but friction takes all that energy away. Well, where does that energy go? If you were able to measure the temperature of the feet of this desk, and you could accurately measure how hot those are, after you slide the desk across the floor, these are going to go up in temperature because the friction causes heat, and that's a type of energy. It's thermal energy. So where did the energy go from the push when you gave it kinetic energy? All that energy goes away from friction in the form of heat. Now, if you're not aware of how friction causes heat energy, here are a couple of examples. If you rub your hands together, you're going to notice they get warm, and that's because of the friction acting between your hands. If you put something on a grinding wheel, notice this very, very hot sparks coming here because when you grind something like that, the friction causes heat. And similarly, if you've ever spun your tires and and you smell the burning rubber, it's because it's burning. It's actually very hot when you spin your tires like that. So friction is a type of thermal energy. Number 5, we're going to describe the energy transformation of a rock. In this case, I couldn't find a picture of a rock, so I found a lady throwing a ball up in the air. And we're going to describe the energy transformation as it goes upward and as it comes back down. So on the left side here, we have on the way up. On the way up, the total kinetic energy never, ever, ever changes. It starts off all as kinetic energy as you throw it, but that kinetic energy is going to go down. It's going to get lower and lower and lower. Why? Because as you throw it upward, it gets slower and slower and slower because it's accelerating downward. And remember, we talked about how kinetic energy can get larger or smaller. If you want smaller kinetic energy, make it go slower. And as the ball rises, or in this case the rock, it's going to be a smaller kinetic energy. But the potential energy is going to go up because it's getting higher and higher and higher. So as it goes higher, the potential energy increases because the H is getting larger. But the total energy never ever changes. So everything that kinetic energy goes down, potential energy goes up. So kinetic energy loses 5 joules, potential energy gains 5 joules. When it reaches the tippy top, it stops moving for just an instant and all the energy is turned into potential. On its way back down, however, it's getting faster and faster and faster and faster as it approaches the ground. So the kinetic energy is going to be getting larger because it's going faster. The potential energy is going to get smaller. Why? Because the height is getting smaller as it falls toward the ground. So as it gains kinetic energy, it loses the exact same amount of potential energy because the total amount of energy does not change. And finally, why is the first hill on a roller coaster always the largest? Well, let's assume that this roller coaster here has just enough energy to get to the top of this very first hill because it just slowly brought it up here. So if we assume there's absolutely no friction, all of the speed it gains going down the hill, it gives that back going back up this hill. Because all the potential energy that it loses in gaining speed and kinetic energy, it's going to give all that potential energy, again, it's going to get it as it loses the kinetic energy as it gets back up to a second hill, which is the same height. So it's got just enough energy to reach this hill because all the energy it had at the beginning is all the energy it's going to have everywhere else along this track. It can easily go up over this hill and get to hill B, where it can go over that because it's got enough energy to reach this height. But notice that if this hill goes to infinity, it goes forever, you're eventually not going to be able to make it up there because if you've only got enough energy to reach a height that's this big, you can only get to about here on this hill because you don't have enough energy to get any higher. Your total energy remains unchanged unless you have some kind of an engine on this car, which roller coasters don't have. You can't get to a higher hill because all the energy you get on the first hill is all the energy you've got for the entire track. So if you do not have enough energy to go to a higher hill, you stop. And that's why the roller coaster maxes out, always has the first hill being the largest to max out your total amount of energy that you have for the entirety of your trip because it doesn't have anywhere else to get energy the rest of the way.